Hello, today we're going to look at the black body radiation and the ultraviolet catastrophe. In my video on the reasons for quantum mechanics, I suggested that it was Einstein who derived the idea that light came in packets of energy, or photons, from the photoelectric effect. But in fact, a few years before that, both Max Planck and Einstein had puzzled over the problem associated with black body radiation. And it was from the solution to that puzzle that really the doorway of quantum mechanics was opened. So it's worthwhile looking at this subject of black body radiation and the supposed ultraviolet catastrophe that I'll describe that actually doesn't arise, and the reason it doesn't arise can be explained by quantum mechanics. But before we deal with black body radiation, I first want to make sure that people are familiar with two things. Firstly, electromagnetic waves, and secondly, the Boltzmann constant, which will both feature in the explanation. First, electromagnetic waves. Well, as the words suggest, it is an electric and magnetic wave, and it travels at the speed of light, which gives you a hint that light itself is an electromagnetic wave. The wave has an electric field, where the electric field goes up and down like this, but it also has an associated magnetic field which is perpendicular to, so it's difficult to draw, but it's kind of at right angles, and it goes like this. So you've got an electric field oscillating up and down this way, and a magnetic field oscillating side to side, as it were, this way. And the whole wave travels in this direction at the speed of light, which is 3 times 10 to the 8th meters per second. The magnetic field is in fact very, very much smaller than the electric field, so I've not drawn this to scale. Now, in any wave, the velocity of a wave can be said to be its wavelength multiplied by its frequency. What I mean is that if this is a wave, the wavelength is the distance between two crests, and it's given the name lambda. The frequency is the number of times a crest passes a given fixed stationary point. So if, for example, the wave which is travelling in this direction has a wavelength of, let's say, 1 metre, and 10 crests pass this point every second, 10 per second, then you can say that the wave travels at a speed v, which equals the wavelength, 1 metre, times 10, which is 10 metres per second. And that's absolutely true for electromagnetic radiation, except that in the case of electromagnetic radiation, the speed is always c, 3 times 10 to the 8th meters per second. And that is equal to the wavelength of the wave times frequency. And you can have any wavelength you like, but of course the frequency will be determined such that the multiplication of wavelength by frequency must always equal c. So as the wavelength goes up, the frequency comes down. And the ranges of electromagnetic radiation are massive. For example, light, as I suggested, is electromagnetic radiation, and the wavelength of light is very approximately 5 times 10 to the minus 7 meters. Some of you may remember BBC Radio 4 used to broadcast on long wave, and long wave was 1500 metres, which means that the wave has a wavelength of just under a mile. That's a long wave. And we can draw a spectrum, it's called the electromagnetic spectrum, showing different waves depending on their wavelength, which increases in this direction, or their frequency, which of course increases in this direction, because as the wavelength increases, the frequency decreases. So at this end you've got low wavelength but high frequency, and at this end you've got high wavelength but low frequency. And at this end you've got cosmic rays, which come out of the sun, followed by gamma rays, which are part of the radioactive radiation, and then X-rays, which go right through you and are used in hospitals, and then ordinary visible light, and then infrared radiation, which is essentially heat, and then microwave, and then shortwave, medium wave, and long wave. These three are typically what used to be used for radio communications. Now, somewhere in this bracket, you've got UHF and VHF, and in many places UHF is what television signals are sent on, VHF is what radio signals tend to be sent off. But this entire frequency spectrum is all electromagnetic radiation. It all travels at the speed of light, but its wavelength is different. At this end, very, very low wavelength, very high frequency. This end, very high wavelength, very low frequency. Next we turn to the Boltzmann constant. This I'm going to describe in terms of a gas in a container. If you have a container with a gas, that gas will have a pressure, it will have a volume, and it will have a temperature. And what you can say about that pressure, volume and temperature in that container is that the pressure times the volume divided by the temperature is a constant. And that means that if you plot P times V against temperature, you will get a straight line. And if you extend that straight line, you eventually get to a point where pressure times volume is 0. And that arises at a temperature of minus 273 degrees Celsius. And we call that absolute zero, because that's the point at which the pressure times volume is itself 0, and you can't go any lower than that. Now, is pressure times volume divided by temperature an absolute constant? Well, obviously not, because it must depend on how much gas you actually have. So what we can say is that pressure times volume divided by a temperature is equal to the number of atoms that there are in the gas times an absolute constant. And that absolute constant is called the Boltzmann constant. And its value is 1.4 times 10 to the minus 23 joules per degree Kelvin. And that gives you a clue. Joules per degree Kelvin relates energy, which is measured in joules, to temperature, which is measured in degrees Kelvin.